Now we have one of my coworkers, Cora Iberkleid, and we also have Gabriella Brodi again, who will be talking about Istio service meshes in conjunction with some existing solutions and seeing how they can work together to improve your system architecture.
Thanks everybody for joining our talk today. We hope you find it useful and interesting. My name is Cora Iberkleid. I'm a part solutions engineer and part developer advocate at VMware.
Hello, everyone, and thank you also for me for being here. My name is Gabriella Brodi, and I am part of the solution engineering team at VMware. I'm excited for this opportunity to talk about gateway and meshes, and without further delays, Cora?
Thank you, Gabri. Okay, so I'm going to share my screen so we can get started here. All right, so the title of our talk is Weaving Through the Mesh, making sense of Istio, or maybe service meshes more broadly, and the overlap that they have with other technologies, some that you might be familiar with, and maybe some of them are new to you. So by way of an agenda, we're going to start with a quick review, not only of the challenges of managing traffic in distributed systems, but also some of the opportunities. And then we'll cover a few different models to address these challenges and the opportunities, ranging from application-based solutions to distributed meshes and broker-based solutions. We're going to briefly touch on where API management solutions fit into the picture, and then we're going to wrap up with some takeaways. So the context for this conversation has to do with distributed systems, right? So distributed systems are not new, but they are becoming more commonplace, right? So if we look back over maybe the last 20 or so years, we've seen an evolution in application architecture, ranging from monoliths to service-oriented architectures that were more often than not still deployed as monoliths, to microservices, where the applications become truly distributed. And there's been a parallel evolution in infrastructure and runtime technologies, starting with virtualization and cloud, to where we are today with containers, and with Kubernetes in particular being the most common container runtime platform. And containerization and microservices go hand in hand, right? So that's led to an explosion in the proliferation of distributed systems. Now, when your application is deployed as multiple individual processes with different processes potentially scaled to multiple instances, you need to deal with the question of how to handle traffic between the different processes. So some of the challenges that you would encounter when you move from monolith to distributed systems are, for example, how does application 1 in this diagram locate applications 2 and 3 so that it can send them requests? Or how might an application load balance requests across multiple instances of the application that it's trying to talk to? What happens, for example, let's say application 4 in this diagram is slow or it's malfunctioning. How do you prevent cascading failures up the stack and still ensure a smooth user experience, right? Or how do you get a clear picture of the behavior of the system, or the full picture of the trajectory of one single request across these applications? So these challenges are not new, and there's many successful solutions available, and we'll talk more about this shortly. But before that, we wanted to point out that as Kubernetes and these overlaying technologies are maturing, there's also opportunities to introduce more sophisticated configuration and behavior. For example, it's becoming easier to do staged rollouts. That's where you deploy version 2 of your application while version 1 is still running, and you progressively shift traffic to version 2. It's also easier to achieve sort of chaos monkey style testing by injecting errors or delays and then checking the resiliency of your system. And it's getting easier to support containerized workloads in conjunction with what you might call heritage virtual machine-based workloads. It's also getting easier to do all of this independently of the language in which your application was written. So we're going to cover a few different approaches that you can use to address these challenges. We're going to talk about application-based approaches, meaning that the application needs to participate in the solution, and also a service mesh approach where the traffic management is handled outside of the application. So let's start with a well-established application-based approach. So let's assume a simple architecture with a UI or front-end application that needs to talk to two back-end services. So in a containerized environment, the endpoint for the back-end services, for example, the IP address, will change if the services are restarted. So we need a way for the UI to dynamically discover a valid endpoint for the services that it needs to talk to. So this is a challenge of registration and discovery. So one common solution is to install a discovery service, and the back-end apps can register their addresses when they start up, and the front end or the UI application can look up these services by name and retrieve their physical location. So then once the UI has the addresses for the back-end applications, it can talk to them directly. But let's say there's multiple instances of A or multiple instances of B, then the UI can also employ a client-side load balancer to distribute the requests across those multiple instances using whatever load balancing algorithm that the developer would like to use. With respect to fault tolerance, it's common practice to wrap a circuit breaker around calls between applications, so around network calls. For example, in this case, the circuit breaker would kick in if service B is too slow or if it's failing. And the front-end application could also use the circuit breaker to define an alternative fallback action in case it can't communicate with service B. And so this helps to isolate the failure, handle it gracefully, and ultimately provide a better end-user experience. In a distributed system like this, it's relatively straightforward to gather the logs of any individual application, but a single user request will traverse all three applications. So in this case, it's common to include a distributed tracing client in each application that can enrich the requests as it goes through the system. And then these unique IDs can be used to correlate information across, say, all three log files so that you can achieve a singular representation of the life of a request through the system. So if you've been working with distributed systems already, you might be familiar with some of the implementations that are out there. And here on this slide, we see some examples within the Java ecosystem. And using something like Spring Boot and Spring Cloud in combination with Netflix or HashiCorp tools makes it really easy to enrich your applications with the necessary functionality. So then we have a slight variation on this approach, which is to include a gateway. So here are the same three applications for our sample application. And this time we have an additional gateway application. So in this example, the UI is not going to connect directly to A or B. And that's a choice that we're making. We're making it go through the gateway to communicate with the backend services. And it's useful because, for example, if A and B are still not fully decomposed from a monolith to a microservice, you can continue to refactor A and B into more microservices. And in that way, you're shielding the UI application from that refactoring you're doing in the background. The gateway also enables us to shift certain responsibilities away from the application. So the responsibility of routing, of load balancing, and circuit breaking can all be concentrated in the gateway. And in this case, you still need the discovery service so that the applications can register their endpoints and find one another. And so, for example, you could use the gateway to expose the application to the end user without exposing a direct connection to the UI application. So that gives you a little bit of added security. So in this flow, the user request would hit the gateway. The gateway would use the discovery service to look up the location of the UI, and then it would send the UI the request. And then the UI is going to go back through the gateway to get to A and B, right? So it would look up the address of the gateway in the discovery service, and then the gateway would complete the interaction with A and B and send the response back to the end user. So for distributed tracing, the solution remains the same with a distributed tracing client still injected into each application. And finally, the gateway also gives us an opportunity to have a central location to handle things like authentication and authorization. It's not necessary to do this in two different gateways, but we've chosen to depict it as two gateways because the authorization gateway on the left is really focused on the security concerns that are probably common to other applications in the organization. And so that's something that might be shared. Whereas the gateway on the right has logic in its routing and its maybe its fallback that are more specific to this particular application. So the same set of implementations is applicable here with the addition of the gateway solutions such as Spring Cloud Gateway or Netflix Zool. Now, some of the advantages of this approach have to do with they provide development teams with autonomy and agility, right? A development team owns the whole solution so that they can deploy it holistically, they can easily iterate on it. And the solution is also consistent with the rest of the application. So, for example, if you work in the Spring ecosystem, it's really easy for you to enrich your applications with circuit breakers, with distributed tracers, to add the discovery server or a gateway to your set of microservices. It all falls within the same Java skill set. So that brings us to the service mesh, and I'm going to hand it over to Gabri at this point. So I'm going to stop sharing. All right.
Thank you very much, Cora. And I am going to start sharing again the screen. We can think about the service mesh as the layer that handles communication between services. And the purpose of the service mesh is to reduce the complexity from the application perspective when it comes to dealing with communication tasks like load balancing, service discovery, security. So the mesh is there to build an infrastructure that is transparent to the workload, and that the workload only need to take care at this point of the business logic. The recurrent approach in Kubernetes world is to use a sidecar for the implementation of the mesh. And each workload that want to be part of the mesh needs to be paired with a sidecar. There are different mechanisms that we can use that can be both manual or automatic to deploy a sidecar with your workload. And the purpose of the sidecar is to interject all the workloads connection, incoming and outgoing. And in this way, it's able to manage this communication, offering the service discovery, the load balancing, and many other capabilities as well. The sidecar knows about the network configuration, the policy, and everything that he needs to know to properly operate, thanks to the control plane that consists of a number of services working together to manage certificates, collects the metrics, provide up-to-date information like the routing table to each sidecar. In this way, every sidecar can communicate with all the appropriate players in the network. As the control plane manages certificate and federation with also other meshes, workloads can count on trusted communication, no matter where they are sitting. The network of sidecar and the communication that are exchanged over it is referred to as the data plane. And this data plane represents all the layer where the network is actually implemented and all the communication happens. Right now, if we look at the top three meshes on the market, we find that Istio, LinkedIn, and Consul are like the most in use. And they share a common set of capability and differentiate or a small subset, like for distributed tracing, fault tolerance. But as we can see, aggregation, the aggregation feature is something that they definitely don't cover. And so it's because this is not part of the networking layer. In general, a service mesh can manage traffic from different perspectives, north-south and also east-west, allowing for really fine-grained traffic management and metrics of collection. And security, and extend the data plane to include traditional VM workloads eventually. And all of this in a transparent way from an application perspective. So it's great, and let's see how can use this capability. So we did this exercise, and we replatformed a gateway-based application to Kubernetes. And what we did essentially is that we took the Color application that is composed by a front end and a number of Color services. There is a Eureka service for discovery gateway and an authentication gateway that is separated. And we decided to replatform this using the path of less resistance. And we did not change the original architecture. So the front end is protected by the authentication gateway, and even in moving to Kubernetes, we are still use the service discovery capabilities from Eureka, and we use the gateway for load balancing and circuit breaking purposes. So the idea was definitely to do as much as possible a lift and shift. So the step that we took were, of course, to put the application in a container. We were able to simplify the service discovery, making more legible, leveraging the service name that's now it's available as we are in Kubernetes. And we also took advantage of environment variable to manage the configuration of the application. And if we take a look at this slide where the configuration is presented, we see now that it is more legible. And like the name of the services, it's really easy to understand who we are talking with. And we can see also the configuration variable that we used to configure each service. And that was it. So this part was easy. So we were able to just replatform, leverage the same architecture that we had before, and things just worked. Now, this is an interesting, a nice view of the Eureka registration, where we can see now how we are pointing to the services when we are using Eureka in the Kubernetes environment. Okay, so that was very nice. Now we want to play with Istio and see what we should do to leverage as much as possible the service mesh capability. We use Istio, like the service mesh of choice is Istio. And let's go back to the original architecture. And so what we did is that from this situation now, we actually end up in a different situation where we said, okay, let's start to remove the services that we don't need. We don't need Eureka because we can do service discovery using mechanisms that are not only embedded in Kubernetes, but specifically we want to leverage the resources from Istio itself. We don't need the gateway. And because the circuit breaking, the load balancing, all of this type of capability, we can leverage Istio for it. And we still kept the authentication gateway as we wanted to maintain for the authentication itself. Now, in these slides, we can see that, okay, we throw some things away and we gain something else. Each service gained a sidecar. And the sidecar in our solution was automatically injected when the pod was deployed. And we used basic resources from Istio to leverage the configuration. So mainly we are going to reference the gateway, virtual service, and destination rule. As a developer, we already used to play with Kubernetes construct. And so like we know the service, we know deployment, replica set. So why not to dive into this new resource that Istio provides? We will get back to this question later, because let's see what happened when we actually work with these resources. Okay, one of the sphere steps. As we removed Eureka, we went and disabled it. And this is what it looks like. Pretty easy. We just changed this part in the configuration. Then, because of this choice, we had to enable the Ribbon client capability to work in conjunction with the Kubernetes services and to handle our communication. And so this required a little bit more of work. First of all, we had to, in order to do this, we had to upgrade our Spring Boot and Spring Cloud so that we can finally add the library and the configuration that was needed. Specifically for Ribbon, as it also implements circuit breaker capabilities, we played with the timeout in order not to mix things with the circuit breaker capability that we wanted to leverage directly in using Istio. Okay, now let's start changing some of the code. And over here, we're addressing the routing first. So this is what the route looked like when we were working with our gateway, and we brought our virtual services. Now that's time also, okay, to look at the virtual service, and we can see that we used the resource, the custom resource definition for the virtual service, and it was a pretty straight translation. Now we move far, and we take a look at the configuration of the asterisk for the circuit breaker. And we see that we have a circuit breaker over here that also have a fallback implementation on it. And we see that when we think about how to implement this in Istio, this was actually pretty easy because we just had to add a line over here to take care of this part. But at the same time, we also realized that we cannot handle callback over here. So the best solution that we had at this point is to go back to our application code and to handle it internally in the application code. And so there are concerns that with Istio, specifically, for example, with the circuit breaker, we were not able to handle easily. And let's say when we need to just implement the pure definition of a circuit breaker, well, that was pretty easy to achieve. Now let's take a look at the application that is actually using two different types of users, a premium user and a basic user. And what it happens is that the application is going to provide to basic users only access to green and blue services, while the premium users have access to premium service, of course, that is made up by the basic service plus the yellow service. Okay, so this is essentially what it looks like for this implementation if we take it in the previous Java context. Now again, we need to change our context, and to do this, we need to go back to our virtual service. And in the virtual service, we decide to do this implementation strictly using the same mechanism with cookies. Actually, there are also other ways that we could leverage, but we decided to stick with the original code behavior. And that was the simplest way. So finally, then we went and we checked the part for default injection. In the original design, default injection was managed through an extra service, the slow green service. So the purpose of the slow green service is just to be there and give a response after a long amount of time. And what we did instead, now that we have access to this new layer and these new resources, is that we were able to add a little bit of configuration in our Istio virtual service and just provide a routing, just change the routing so that in 30% of the time, just based on what was the original behavior, there is going to be a delay in the response, exactly the same type of the delay that we were looking at before. And as you can see, there was again some context switching between, of course, the Java and the code in the Istio. So what did we experience? Okay, some switching of context, not only because we wanted to translate things, but also because some of the things like the callback in the circuit breaker, we actually had to implement back in the service. And we saw that, for example, configuration changes were pretty fast without the need of redeploying the application itself. We can change the configuration of the virtual service, just apply it, and it's going to happen without any change to the application. On the other side, when it was about debugging, that introduced a new layer of difficulty, and we have to play with a different number of tools, and like that experience was a little bit more complex to the one that we were used before, just to be able to debug at the network level, and we have to introduce more tools in our basket. So we did not even talk right now in the exercise that we did about certificates and how, for example, Istio solved the problem of trust between applications that are running across namespaces and cluster. So this was just a simple case with just a really reduced set of features. But still, we can already see and appreciate a lot of the advantages and possibility as well as challenges, and the extra burden that now there is on the developer's shoulder. The resources that we use to configure the cluster, who owns those resources? The same place where we are configuring our routing are places where we can define mutual TLS. So do we want to have access for both the operator and the developer exactly on the same resource? How do we separate this persona? So looks like there are some gray area over here. And for a view on the application, application-based approach using RSocket, I'm going to switch back to Cora.
Great. Thank you, Gabri. Okay, so let's continue. I'm going to share my screen again here. And there we go. All right. So the last model we wanted to talk about was an application-based model using RSocket. So we'll talk about RSocket and how we can use an RSocket broker to create our own mesh of sorts. So first of all, what is RSocket? So RSocket is a communication protocol. It's based on a specification called reactive streams. And the reactive stream specification was a joint effort across a few different companies to create a standard for asynchronous stream processing with non-blocking back pressure, which I know is a mouthful, but I'll try to clarify in the next few slides. So although you might be familiar with reactive streams already if you've done any reactive Java programming, so that's reactive behavior within a single JVM, for example, a single process. With RSocket enables reactive behavior in the communication between processes at the protocol level. And so in that sense, it kind of aligns with the spirit of the service mesh, and that it aims to push the handling of some of the concerns that we've been discussing down to the protocol layer. RSocket is very efficient. On the one hand, it establishes and it reuses a single connection between two applications. And on the other hand, the transfer of data itself is very efficient. So it moves binary data. It doesn't care what the payload is. And it transports messages in a multiplexed manner. So the order of the responses doesn't matter. It supports the traditional interaction types. So request, reply, fire and forget, where you send a message, you don't need the response back, or request and get a stream of messages back. And it also supports streams in both directions. So if you think about some of the apps that you might have on your phone, for example, that need to send and receive streams of data, the ability to do this on a single persistent connection is pretty powerful and significant. So let's take a moment to compare RSocket to HTTP, just to put it in terms of something that might be more familiar. So overall, HTTP is improving, but RSocket is considerably more efficient and responsive. So RSocket establishes, as we said, a single, shared, long-lived, or persistent connection, which is much better than establishing a new connection for every request, right? Usually the most expensive part of a transaction in terms of time is the connection time. RSocket also multiplexes messages over that connection. So with multiplexing, as I mentioned, a client can receive responses in any order, which is significantly more efficient than pipelining, where the client needs to get the responses in the same order as the requests. And then with HTTP, there's no way to communicate how much load a process can handle and adjust accordingly. Instead, you end up with maybe a broken connection or a status code or like a 500 internal server error or something along those lines, right? But with RSocket, there's this concept of back pressure that comes from the reactive streams spec. So an application can communicate to the other one how much it can handle, so to control the data flow. And so kind of maybe similarly to a fallback action with a circuit breaker, when an application gets a signal of back pressure, it can adapt accordingly. So if you think about maybe like a streaming service, maybe the streaming service would switch to a lower quality stream, right? And then the traditional client-server relationship is more flexible with RSocket. So either party can initiate a request. It supports bidirectional streaming. And again, think of maybe a navigation application that's uploading information about your movement and also downloading streams about traffic. And that can happen over a single connection, and either side of that exchange can initiate new interactions, new requests. And then finally, RSocket supports canceling streams. So you can't do this with HTTP, right? Once you send a request to a server, there's no way to take it back. But with RSocket, you can cancel. And you can also resume streams if they're disrupted. So imagine like switching Wi-Fi networks and a connection drops. It's much more efficient if you can just pick up where you left off when you get a new connection. So altogether, this means that RSocket is not only much faster, but it can also represent a significant amount of cost savings in bandwidth and in infrastructure. So what applications can use RSocket? So there's driver implementations for a few different languages, including JavaScript, which is really interesting because it means that you can make an RSocket connection from your browser, right, with using WebSocket over HTTP. And so RSocket by itself enables us to make a connection between two processes. But what happens when you want to scale, right? Does that mean that you have to establish point-to-point connections between all instances? And even if you did do that, how would you distribute traffic? And it raises all of the same questions and concerns that we had earlier about distributed systems. So this is where an RSocket routing broker can be really useful. So each process becomes a client to the broker, right? Each process connects to the broker, and then the broker kind of just naturally becomes its own discovery server, right? It knows these connections are persistent, so it knows where all of these clients are. So any process that wants to initiate a request needs to send its payload plus some additional routing metadata to the broker to tell the broker how to forward the message. So for example, what app to send it to, whether to broadcast to all instances of the receiving application or just unicast to a single instance, maybe even be specific about which instance to send it to. The broker also naturally kind of takes on the responsibilities of load balancing. It's useful as a central point for collecting metrics and monitoring information. Also, it can communicate back pressure. So if A and B need to communicate back pressure to each other, RSocket forwards that signal. But also, if, let's say, service B is down entirely, there are no instances of service B, and service A is trying to send messages to service B, the RSocket broker can just apply 100% back pressure to service A instead of having service A experience a no host or something like that. The broker applies 100% back pressure, and then service A can decide how to gracefully handle that information. The broker can also be clustered. So in this case, the connections between the clients and the broker nodes are, of course, they're still persistent. So if a requester and a responder apps are connected to different cluster nodes, then the cluster nodes pass the messages to each other to get it to the correct node in order to reach the destination app. And then it does the same with the response on the way back. So it's an extra hop, but the effect is negligible because compared to all of the efficiencies that are inherent to this model, that extra hop is really insignificant. So at scale, you can really see the benefits of this in terms of speed and in particular cost savings. There's some talks online that mention some of the savings that companies like Twitter, for example, have made, and the numbers are really staggering. So the broker capabilities on top of the simple RSocket are being developed under this project called RSocket routing. And the broker, it's really easy to use. There's like minimal configuration to provide, if any, and you can just deploy it, and then you just tell the clients where the broker is. And this project is based on what was formerly known as Spring Cloud RSocket, and it also includes the code base that was also formerly being deployed by a startup called Netify. So now those two code bases are merged and they're being actively worked on. But one note about this, I'll just say that the RSocket drivers that I mentioned in the previous slide, those are mostly at version 1.0, and this routing broker is still a little newer than that. So it's early stages, not GA yet. And this model offers kind of the same, some of the same advantages that we saw earlier with the application-based models, the same autonomy, the same agility and consistency and skill set required from the point of view of development teams. But in this case, there's also some additional advantages, which namely the speed and the cost savings from less use of bandwidth and infrastructure. So in continuation with this theme of an exercise of replatforming, we did a replatforming exercise with an RSocket broker-based application also. So we had a cluster of brokers and an application called Ping and an application called Pong. Ping sends a stream of pings to Pong, and Pong sends a stream of Pongs to Ping. And this image is just depicting this deployment at scale. It's really three container images, three different types of applications, the Ping, the broker, and the Pong. But this is scaled to a few different instances for each one of those. So the first part of the setup is to set up the cluster itself. So the nodes in the cluster need to communicate two kinds of information with each other. They need to tell each other which apps are connected to them. And then they also need to forward traffic from apps to each other, right? To get the client traffic to the right destination. So we can think of this as sharing admin data versus passing around client traffic. So for the admin data, we configured these nodes to use port 7002. And for the client traffic, we're using port 8002 to differentiate the two. So each broker node gets its own service in Kubernetes. So we have a service called Broker 1, another Kubernetes service called Broker 2, and another one called Broker 3. But otherwise, they're all the same. In Kubernetes, of course, port management is a non-issue, so they all can listen on port 7002 and 8002, which makes it easier than a sort of a local deployment. And these three services, Broker 1, Broker 2, and Broker 3, are going to be used exclusively by the broker nodes to talk to each other. They're not going to be used by Ping and Pong. So this is some of the configuration. The Spring configuration on the right-hand side tells the node which other nodes exist in the cluster so it connects to. So the right-hand side is the Spring app configuration for startup. And it differentiates, as you can see, between a cluster and a proxy port. So that cluster port, 7002, is for the admin data, for the nodes to share who's connected to them. And the proxy port is for them to pass client traffic to each other. So that's 8002. And on the left-hand side, we can see the configuration of the Kubernetes deployment of each node, where we're dynamically populating those environment variables that are used in the Spring application YAML with the name of the services. So each one uses the name of the other two that don't represent itself, right? So it's pretty straightforward. And you can see that it would be pretty simple to add a fourth node to this cluster, but you would need to update each deployment YAML with an additional environment variable. And you would need to update the Spring configuration file. But in the future, this is going to get simpler so that, for example, adding a new node, every node would be able to get information about the whole cluster from just one other node. So then it would be trivial to add nodes to the cluster. So then from the perspective of configuration of the communication for the client applications, ping and pong to the cluster, that's super simple. You just need to create a single service that fronts the entire cluster. So just a generic broker service, port 8002. And that service will load balance connection requests from ping and pong to any of the cluster nodes. It doesn't matter which one. And so that ping and pong will only go through that service the first time. And it's in order to establish a direct connection to the node. Once that connection is established to the node, then they just start communicating with the broker directly, right? And so you can see that on the bottom left, for ping and for pong, the configuration would be to use the name of the Kubernetes service as the host name, right? So it's pretty cool. It's very simple to run on Kubernetes, and it's very efficient, as we said. So this technology is new, but it's really interesting. So good thing to keep your eye on. And that brings us to API management solutions. And I'm going to hand it back to Gabri for that and actually to close out the talk.
Thank you very much, Cora. And so here we go again. We felt that we also need to talk about the API management. And let's give just a quick overview for this solution. Usually, these solutions are deployed at the very edge of your organization, between your customer and your services. And they can serve multiple domains and respond to multiple needs. And those are like centralizing operations that are common between applications, like the security, the authentication, the routing, and also acting as adapter, so that exposed API and internal implementation can be different, but also and mainly probably collect metrics on consumption and quality of services for the business perspective. And a lot of the API governance sits in here. And we can say that these metrics are mainly responding to billing needs, as they are so decentralized. There isn't a self-service at this level, and usually there is an indirect interaction between the tool that is maintained by other teams, and often changes are requested through ticket system. A lot can be implemented and controlled here at the expense of being remote, respect where the services are actually running. And our takeaways. So, what is our takeaway? Well, in summary, in the realm of traffic management for distributed application in Kubernetes, there are a lot of tools, often with a broad range of responsibilities. And the more sophisticated, like meshes, they bring value for crucial business case, from business continuity. Let's think about failover and like multi-cloud or hybrid cloud configuration, to end-to-end and mutual transport layer security, to rolling upgrades at scale, and also in a situation where you need to predict the average response of the network, and challenging environment like exactly the hybrid or the multi-cloud, where latency matters and you need to keep that really under control. And they do this in a distributed fashion, exactly at the doorstep of the service that needs to use it. On the opposite side of the spectrum, there are the API management solutions that provide a centralized approach, usually at organization level, with a lot of guardrails. And then we have Spring Cloud Gateway and RSocket brokers that are deployed closer to the application. And they offer really easy access to the developers. In conclusion, about the mesh, go play with it. Have fun, for sure, in experimenting. The effort, though, to onboarding technologies like the meshes is appropriate when there is a business case, a solid one for it. Don't use this unless you really need it. It's going to add complexity and risk and need organizational maturity and access to more sophisticated tools for their management. The mesh alone isn't enough when we think about scale. There are open source and commercial tool offering that address these gray areas. For example, Spring Cloud Gateway and Tanzu Service Mesh are ready to provide solutions at scale for developers and operators and cover for those gray areas that we spoke about before. And because of this, with this thought in mind, we feel that would be good if we would suggest to follow also this following track that can help shed more light on what is coming to help defining your strategy. And specifically about the main stage talk tomorrow from Bella and Chris, the introduction to Spring Gateway by Alexei and Gareth, and the service mesh, the talk around service mesh for Deepa and Ramiro. And of course, we need to say a special thanks for all the insightful conversation to James, Deckel, Spencer, Chris, Pere, Manish, and John. And a special thank to you as well for being here.